what lies just beyond the horizon of our solar system? Our closest stellar neighbors offer a glimpse into the vastness of the cosmos, yet their proximity challenges our understanding of distance and scale. The Alpha Centauri system, our closest interstellar neighbor, is a triple-star system that holds tantalizing possibilities for exploration. Among its members is Proxima Centauri, the nearest star to Earth, a small red dwarf harboring a rocky exoplanet, Proxima b, that sits in its habitable zone. Could it support life, or do its intense solar flares render it barren? To put this journey into perspective, consider this. Reaching the Moon takes just a few days, and traveling to Mars requires months. Yet, to reach the stars, the scales are different. Alpha Centauri sits a staggering 4.37 light-years away, a distance so vast that even our fastest spacecraft would take over 70,000 years to arrive. What lies in those unthinkable gaps of time and space, and how do we even begin to bridge them? Join me as we explore the journey to reaching the nearest stars, the cosmic neighborhood. Our celestial neighborhood contains a variety of stars, but only a select few lie within what we consider close proximity. The Alpha Centauri system holds the distinction of being the closest. This triple-star system consists of Alpha Centauri A, Alpha Centauri b, and the Proxima Centauri, each with unique characteristics. Proxima Centauri is the closest star to Earth, at a distance of 4.24 light-years. It's a red dwarf, smaller and cooler than our Sun, yet capable of hosting planets like Proxima Centauri b, a rocky exoplanet located in the star's habitable zone. This zone represents the region where conditions might allow liquid water to exist. Proxima b is only slightly larger than Earth and orbits its star every 11.2 Earth days. However, its proximity to a red dwarf poses challenges. Intense solar flares and radiation might strip its atmosphere over time, reducing its potential habitability. When considering distance, most of us think in manageable terms, miles, kilometers, or even astronomical units, AU, the average distance between Earth and the Sun. But interstellar distances defy our everyday understanding. The nearest stars are so far away that measuring them in kilometers becomes almost meaningless. Instead, astronomers use light-years, the distance light travels in 1 year, about 9.46 trillion kilometers. For context, let's compare this to familiar scales. The Moon, the closest celestial body, is 384,400 kilometers away, reachable in just over 3 days by spacecraft. Mars, depending on its orbit, might be as close as 54.6 million kilometers, or as far as 401 million kilometers. Reaching Mars is a months-long endeavor, yet this is still a short hop compared to the journey to the nearest star system, Alpha Centauri, which is located approximately 4.37 light-years away. At current spacecraft speeds, like those achieved by the Parker Solar Probe, which travels at around 700,000 kilometers per hour, it would take over 70,000 years to reach Alpha Centauri. This staggering time frame shows the immense challenges humanity faces in its dreams of interstellar travel. It's not simply about distance. It's about overcoming the barriers of time, energy, and technological innovation. The other two stars in the Alpha Centauri system, Alpha Centauri A and B, form a binary pair. They orbit a common center of mass, providing a dynamic gravitational environment. While they don't have confirmed planets, their proximity makes them prime candidates for future exploration. Beyond the Alpha Centauri system, several other nearby stars captivate astronomers with their unique characteristics and potential for exploration. Barnard's star, a red dwarf located 5.96 light-years away, stands out as one of the fastest-moving stars in the sky relative to our solar system. It hosts Barnard's star B, a possible exoplanet situated just beyond its habitable zone. Slightly farther out, at 7.8 light-years, lies Wolf 359, a faint red dwarf that challenges observational efforts but offers a valuable opportunity to study the dynamics of smaller, cooler stars. At 12.36 light-years away Luyten's star presents another exciting target, with its own potentially habitable exoplanet, Luyten b, adding to the growing list of intriguing nearby systems that might one day expand humanity's understanding of the cosmos. Before we can journey to the stars, we must first understand them. Observing and studying stars involves overcoming the limitations of distance, brightness, and interference from Earth's atmosphere. Astronomers rely on a combination of techniques and technologies to unlock the secrets of our cosmic neighbors. The first challenge is determining how far away these stars are. Parallax, the apparent shift of a star's position against the background of more distant stars as Earth orbits the Sun, is the foundation of distance measurement. By measuring this tiny shift and applying geometry, astronomers calculate a star's distance with remarkable precision. For stars within a few hundred light-years, this method remains the most reliable. The light from a star contains a wealth of information. Spectroscopy involves splitting starlight into its component wavelengths, revealing the star's temperature, chemical composition, and motion. For example, a star's wobble, caused by the gravitational pull of an orbiting planet, can be detected as shifts in its spectral lines. This technique has been crucial in identifying exoplanets like Proxima b and Luyten b. Ground-based telescopes face limitations due to atmospheric distortion. Space telescopes like Hubble, Kepler, and James Webb overcome these obstacles, providing unparalleled views of nearby stars and their planets. The James Webb Space Telescope in particular has the ability to analyze exoplanet atmospheres for potential biosignatures like oxygen and methane, advancing the search for habitable worlds. Directly imaging exoplanets is one of astronomy's greatest challenges. Future instruments, such as the proposed LaVoire telescope, aim to capture detailed images of planets around nearby stars, revealing their surface conditions and atmospheric makeup. Human curiosity about the stars dates back millennia. Ancient civilizations, such as the Babylonians, Egyptians, and Greeks, viewed stars as immutable points of light, each holding spiritual or mythological significance. Early astronomers like Aristarchus of Samos and Hipparchus attempted to measure the heavens, laying the groundwork for future discoveries. It wasn't until the Renaissance, with the invention of the telescope, that humanity began to truly understand the nature of stars. Galileo Galilei, in 1609, turned his telescope to the heavens and shattered the ancient belief of stars as unchanging entities. He observed the Milky Way as a dense collection of countless stars, proving the universe was far larger and more complex than previously imagined. Fast forward to the 19th century, when William Herschel mapped the positions of stars and proposed that the Sun was part of a larger galactic system. This perspective shifted humanity's view, placing our solar system within the grander scale of the cosmos. The advent of spectroscopy in the mid-1800s, pioneered by Gustav Kirchhoff and Robert Bunsen, allowed astronomers to analyze starlight and identify their chemical compositions for the first time. These advancements culminated in the 20th century, with the realization that stars like Alpha Centauri were not just distant points of light, but other suns, some with potential planetary systems. The discovery of the exoplanets in the 1990s, starting with 51 Pegasi b, opened the door to the idea of other habitable worlds. These breakthroughs inspire the modern search for understanding and possibly reaching the nearest stars. Astronomy isn't solely the domain of professional scientists. Citizen science projects have democratized the process, allowing individuals to contribute to groundbreaking discoveries. Platforms like Zooniverse enable enthusiasts to examine data from telescopes and identify potential exoplanets, variable stars, or transient phenomena. One notable example is the discovery of Tabby's star, an enigmatic star with unusual dimming patterns by participants in the Planet Hunters project. Although not within our nearest stellar neighborhood, it highlights how collaborative efforts can yield unexpected insights. Engaging the public also amplifies awareness and appreciation for the challenges of studying distant stars. Understanding the nature of nearby stars involves exploring their life cycles as they represent various stages of stellar evolution. These stars offer valuable insights into how stars form, live, and ultimately die, contributing to our understanding of the universe. Red dwarfs, such as Proxima Centauri, dominate the cosmos, accounting for about 70% of all stars. These small, cool stars burn their fuel so slowly that their lifespans can extend to tens of billions of years, far surpassing stars like our Sun. Despite their stability, red dwarfs like Proxima Centauri pose challenges for life due to their intense solar flares, which could strip away planetary atmospheres in their habitable zones. Sun-like stars in the Alpha Centauri system, particularly Alpha Centauri A and B, showcase a more familiar stage of stellar evolution. With their brightness and stability, these stars provide an excellent environment for studying the formation and evolution of planetary systems similar to our own. Dying stars such as Sirius offer a glimpse into the ultimate fate of stars like the Sun. Sirius, the fifth closest star system, includes a white dwarf companion, Sirius B. This dense stellar remnant, the collapsed core of a once massive star, serves as a natural laboratory for examining the final stages of stellar life. The journey to the stars is far from empty, as the interstellar medium, ISM, fills the space between stars with tenuous gas, dust, and radiation. Though seemingly sparse, the ISM plays a pivotal role in the life cycles of stars and planets, acting as both a cradle for new stars and a challenge for interstellar exploration. In regions of dense ISM, gravity causes gas and dust to collapse, igniting nuclear fusion and giving birth to stars. Observing these nurseries, such as the nearby Taurus molecular cloud, reveals the processes that formed stars like Proxima Centauri billions of years ago, shedding light on the origins of stellar systems. However, the ISM is not a tranquil vacuum. It is a harsh environment filled with cosmic radiation, magnetic fields, and high-energy particles. For a spacecraft heading toward Alpha Centauri, even the low-density particles and dust present in the ISM could pose significant hazards. Traveling at high velocities, these tiny particles could erode or damage a spacecraft's surface, necessitating advanced shielding and innovative engineering solutions. Beyond its challenges, the ISM also holds tantalizing clues about the building blocks of life. Organic molecules detected within the ISM suggest that the precursors to life may be widespread in the universe. By studying these molecules, scientists gain valuable insights into the chemical conditions that could foster life around other stars. Technological advancements are pushing the boundaries of what's possible in studying and reaching nearby stars. Concepts like Breakthrough Starshot, a project aiming to send tiny spacecraft to Alpha Centauri at 20% the speed of light, could revolutionize interstellar exploration. These light-sail spacecraft, propelled by powerful lasers, might reach Proxima Centauri in just over 20 years. Another promising avenue is interferometry, combining the light collected by multiple telescopes to simulate a much larger aperture. Projects like the European Space Agency's Gaia mission, which maps the positions and motions of stars with unparalleled precision, are laying the groundwork for even more ambitious projects. Parallax and spectroscopy in observation. Parallax and spectroscopy have been key tools for unraveling the mysteries of the universe, especially when it comes to understanding our closest stellar neighbors. These techniques allow us to determine distances, compositions, and even the motion of celestial bodies, laying the foundation for interstellar exploration. Parallax is a straightforward yet precise method for measuring stellar distances. By observing a star's apparent shift in position relative to background stars as Earth orbits the Sun, astronomers can calculate its distance. This concept relies on geometry and the size of Earth's orbit as a baseline. However, even for the closest stars, such shifts are tiny, less than 1 arcsecond for Proxima Centauri, the nearest star to us. Capturing such minute angles requires highly sensitive instruments, like the Gaia Space Telescope, which has revolutionized our understanding of stellar distances. One way to enhance parallax measurements in the future is by extending the baseline beyond Earth. Observations from the Moon or Mars, where orbits differ significantly from Earth's, could increase the accuracy of distance calculations. Larger baselines mean finer precision, enabling astronomers to probe deeper into nearby regions of the galaxy. When traveling long distances, the effectiveness of parallax decreases. At distances beyond a few thousand light-years, the resulting angles are too tiny to be measured with present-day technology. Standard candles like Cepheid variables are used by astronomers for more distant stars and galaxies. For it comes to close systems, though, parallax is still unrivaled, providing unrivaled clarity for measuring stars like Alpha Centauri. For exoplanet systems, parallax provides critical information about the size and distance of planets orbiting other stars. By combining parallax with other methods, such as transit photometry, scientists can better understand the potential habitability of these worlds. Additionally, parallax measurements paired with proper motion data reveal the trajectories of stars. For instance, understanding how stars have moved relative to the Sun helps reconstruct the Milky Way's dynamic history, including past stellar flybys that may have influenced our solar system. Spectroscopy complements parallax by focusing on the light emitted or absorbed by celestial objects. This technique involves splitting starlight into its component wavelengths, revealing the chemical composition, temperature, and motion of stars and planets. Spectroscopy works across various wavelengths, from visible light to ultraviolet and infrared, each providing unique insights. For instance, studying the infrared spectrum can reveal cooler objects like exoplanets or regions obscured by interstellar dust. One of the most valuable aspects of spectroscopy is its ability to detect chemical fingerprints. Every element emits or absorbs light at specific wavelengths, leaving behind spectral lines that act as a signature. By analyzing these lines, astronomers can determine what stars and planets are made of. For exoplanets, spectroscopy is particularly powerful when studying atmospheres. Observing the light passing through an exoplanet's atmosphere during a transit can reveal gases like oxygen, methane, or water vapor, potential indicators of habitability or even life. Spectroscopy also plays a critical role in understanding stellar motion through the Doppler effect. When a star moves toward or away from Earth, its light shifts in wavelength. This redshift or blue shift reveals the star's velocity along our line of sight. These subtle shifts have even been used to discover exoplanets, as the gravitational tug of an orbiting planet causes the host star to wobble slightly, producing periodic changes in its spectral lines. Beyond individual stars, spectroscopy has applications on cosmic scales. By measuring redshifts, astronomers determine how fast galaxies are moving away due to the expansion of the universe, providing a window into its history and ultimate fate. But even within our stellar neighborhood, spectroscopy offers valuable data. For example, it helps disentangle the light from multiple stars in systems like Alpha Centauri, where two bright stars orbit a common center of mass. In star systems with pulsating variable stars, such as Cepheids, spectroscopy and parallax work together. Parallax provides the distance, while spectroscopy reveals the star's pulsation period and its link to intrinsic brightness. Together, these data refine the cosmic distance ladder, extending our ability to map the universe. Innovations in technology have significantly improved both parallax and spectroscopy. Laser interferometry and adaptive optics have enhanced the precision of parallax measurements, while space-based observatories eliminate atmospheric interference for spectroscopy. Ground-based instruments, despite limitations from Earth's atmosphere, still play a vital role by using sophisticated techniques to correct distortions and collect valuable data. Navigating interstellar space, however, comes with challenges. Dust clouds and gas can scatter and absorb starlight, complicating both parallax and spectroscopy measurements. Yet, this interference also provides opportunities to study the composition and density of the interstellar medium, enriching our understanding of the material that connects stars. Parallax and spectroscopy have historical roots that demonstrate their enduring significance. The first successful parallax measurement, achieved by Friedrich Bessel in 1838 for the star 61 Cygni, marked a milestone in astronomy. Similarly, the early use of spectroscopy to study the sun and stars laid the groundwork for uncovering the universe's chemical and physical properties. Spectroscopy even reveals the surface features of stars. Variations in spectral lines over time can indicate phenomena like star spots, cooler, magnetically active regions on a star's surface. These observations provide insights into stellar rotation, activity cycles, and magnetic field dynamics. The Gaia mission has taken parallax to unprecedented levels, mapping over 1 billion stars with remarkable accuracy. This vast dataset offers a three-dimensional view of the Milky Way, reshaping our understanding of its structure and motion. Similarly, spectroscopy has advanced our ability to study star-forming regions, identifying the chemical building blocks of stars and planets. The light speed barrier. The speed of light is often referred to as the universe's ultimate speed limit, a rule set in place by Einstein's theory of relativity. This rule states that nothing with mass can ever reach or exceed the speed of light, approximately 299,792 kilometers per second. For us on Earth, this poses a challenge when imagining journeys to the nearest stars. Even with the fastest spacecraft humans have built, we are nowhere near this limit, and understanding why requires digging into both physics and the vastness of space. As an object moves faster, it gains energy, and this energy adds to its effective mass. The closer the object gets to the speed of light, the more energy is needed to accelerate it. This relationship isn't linear, it's exponential. At 90% of the speed of light, the energy needed is enormous. At 99%, it becomes nearly impossible with any technology we currently have. To accelerate a spacecraft even close to light speed would require energy outputs beyond anything humans can generate. This brings us to time dilation, another consequence of Einstein's relativity. At speeds nearing light, time for those on the spacecraft slows compared to those left behind. For example, a journey that takes years for the crew might feel like only months or weeks on board the spacecraft. While this sounds beneficial for space travelers, it creates a gap in how events unfold for those on Earth versus those in the spacecraft. For interstellar missions, where communication and coordination are vital, this distortion of time presents a significant challenge. The speed of light also anchors the concept of causality, the relationship between cause and effect. If something could travel faster than light, it could theoretically create paradoxes where an effect happens before its cause. This kind of disruption isn't just philosophical. It would mean rewriting the very laws that govern the universe. Scientists believe that causality must remain intact for the universe to function as we understand it, further reinforcing the light speed barrier. Photons, the particles of light, naturally travel at this ultimate speed because they have no mass. However, everything else in the universe, from atoms to spaceships, does have mass, which ties them to speeds much lower than light. This is why photons can travel vast cosmic distances, allowing us to observe stars and galaxies billions of light-years away. Yet, despite their incredible speed, even photons are bound by time, taking years to reach us from distant objects. Interestingly, there are scenarios where particles appear to exceed the speed of light in specific conditions. In a medium like water or glass, light slows down compared to its speed in a vacuum. When a charged particle moves faster than light's reduced speed in that medium, it produces a phenomenon called Cherenkov radiation. This creates a bluish glow, often observed in nuclear reactors. While this doesn't violate relativity, it highlights how the speed of light remains an unbreakable boundary in a vacuum. The Higgs field also plays a role in why objects cannot reach light speed. This field gives particles their mass, and without it, particles like photons remain massless, allowing them to achieve light speed. For massive particles, however, the Higgs field acts as a kind of resistance, preventing acceleration to such extreme velocities. This resistance is a fundamental part of how the universe operates. But what about the expansion of the universe itself? After the Big Bang, the universe underwent a phase of rapid inflation, where space expanded faster than the speed of light. This might sound like it contradicts the light-speed barrier, but it doesn't. During inflation, it wasn't objects moving through space that exceeded light speed, it was space itself expanding. This distinction allows for faster-than-light expansion without breaking relativity's rules. Similarly, gravitational waves, ripples in space-time caused by massive cosmic events, also travel at the speed of light. These waves are crucial for understanding phenomena like black hole collisions. Their behavior reinforces the universality of the light speed limit, showing that even disturbances in space-time cannot surpass it. When it comes to practical propulsion, the light speed barrier is a massive hurdle. Accelerating a spacecraft to even a fraction of light speed would require energy levels far beyond our current capabilities. For instance, achieving 10% of light speed might require the entire world's annual energy output. This is one reason scientists are exploring alternative propulsion methods like solar sails or antimatter engines to bypass traditional fuel constraints. Cosmic rays provide natural examples of particles traveling near light speed. These high-energy particles, originating from events like supernovae, race through space at incredible speeds. While they approach light speed, they never reach it, illustrating the energy limitations that even nature imposes. Observing these cosmic rays helps scientists understand the challenges of high-speed travel and how particles behave in extreme conditions. The relationship between the light speed limit and information transport is one of the most intriguing features of the phenomenon. Any attempt to communicate with faraway spacecraft will be severely delayed due to the fact that signals and messages are similarly constrained by this restriction. If we were to send a message at the speed of light, it would take more than 4 years to reach the closest star system, Alpha Centauri. Autonomous systems would have to work independently due to this latency, which would make real-time contact with interplanetary missions unfeasible. Quantum entanglement, often mistaken as a way to bypass the speed of light, doesn't actually allow faster-than-light communication. While entangled particles share a mysterious connection, no usable information can be transmitted between them instantaneously. This keeps the light speed barrier intact, even in the strange realm of quantum mechanics. Even our understanding of light itself is shaped by the speed barrier. When we observe distant galaxies, we see their light as it was billions of years ago. This look-back time reveals the universe's history, but it also reminds us of the vast distances that separate us from other stars. Light speed may be fast, but it isn't instantaneous, which shapes our perception of the cosmos. Theoretical concepts like the Alcubierre warp drive suggest bending space-time itself to achieve effective faster-than-light travel. Instead of moving a spacecraft through space, this method involves compressing space ahead of the craft and expanding it behind. While this idea is mathematically intriguing, the energy requirements are astronomical, involving exotic materials that may not even exist. Practical spacecraft face material and engineering constraints. At near light speeds, even tiny particles in space become dangerous projectiles. The energy from a collision with a micrometeoroid could destroy a spacecraft. This means shielding and impact-resistant designs are essential for any high-speed missions. The light speed barrier isn't just a physical limit. It's a guiding principle that shapes how we think about the universe and our place in it. It challenges us to innovate, pushing the boundaries of science and engineering, while reminding us of the scale and complexity of the cosmos. Time dilation in interstellar travel. As we delve into the possibilities of interstellar travel, time dilation emerges as one of the most intriguing concepts, reshaping how we understand space, time, and the universe's natural laws. Unlike Earthbound time, which ticks predictably, Time dilation warps the passage of moments depending on speed and gravitational influence. For travelers venturing to the nearest stars at relativistic speeds, this phenomenon becomes a defining aspect of the journey. Time dilation is not merely a slowdown, it changes perception itself. Travelers moving at near-light speeds would witness celestial phenomena unfold differently. Stars and galaxies that Earthbound observers see as slow and steady might appear accelerated. This altered perception isn't just visual. It impacts how onboard scientists interpret cosmic events, pushing the limits of observational science. Changes to the cosmic microwave background radiation stand out as an especially noticeable consequence. When traveling near the speed of light, it would change from being invisible to higher energy wavelengths, which might include dangerous X-rays. Both cosmic rays and this unanticipated danger from the radiation of the early cosmos would necessitate shielding measures for spacecraft. For the human body, time dilation could create conditions that have never been experienced. Biological processes like aging, DNA repair, and cell regeneration might appear slowed down relative to Earth time. However, this raises new questions. Do slower biological processes under time dilation come with unknown risks? Could DNA integrity be altered in ways we cannot yet predict? These remain speculative but essential topics for future research. The human brain also faces challenges. Memory encoding and perception might adjust to prolonged relativistic conditions. How would cognitive function adapt when travelers experience a compressed timeline compared to those on Earth? Simulated time environments on board may provide some psychological grounding, but this doesn't eliminate the profound mental effects of such a journey. The relativistic Doppler effect compounds the challenge of time dilation. Light from nearby stars would shift dramatically, causing changes in color and intensity. For travelers, this means the starlit universe they observe may appear entirely different. Blue-shifted stars could seem brighter or more menacing, while red-shifted objects fade from visibility. These shifts would also affect how instruments capture data, requiring recalibration to account for these new wavelengths. Beyond light, signals between the spacecraft and Earth would stretch or compress. Communication systems must adapt to manage the changing frequencies and ensure clarity. Decoding these signals becomes an engineering feat, one essential for maintaining contact over the vast distances of space. Navigating through the stars while experiencing time dilation requires a recalibration of every assumption about travel. Pulsars, often used as cosmic lighthouses, emit regular radio bursts that may appear distorted to travelers. Calculations for trajectory corrections must account for both the spacecraft's velocity and the changes in observed pulsar signals caused by time dilation. High speeds compress the perception of celestial events. A traveler might observe an accelerated sequence of events, such as the life cycle of stars or the merging of distant galaxies. While breathtaking, these accelerated views complicate navigation and demand predictive models that account for the relative motion of celestial objects. Ironically, time dilation offers a surprising advantage. It can help interstellar travelers avoid certain risks. Small particles like micrometeoroids, which move at deadly speeds, pose a constant threat to spacecraft. However, from the perspective of a time-dilated traveler, these hazards might move too quickly to cause significant damage. Nonetheless, spacecraft must still prepare for the unexpected, reinforcing structures to withstand impacts at relativistic speeds. Radiation exposure, however, remains a persistent danger. As travelers compress time, the intensity and frequency of cosmic radiation shift. Protective measures like magnetic shielding or graphene-based materials will play a critical role in ensuring crew safety. Interestingly, not all systems on board a spacecraft experience time dilation equally. Slight variations in position, speed, or even gravitational pull could desynchronize different parts of the ship. For example, a propulsion system operating at the rear of the spacecraft might experience slightly different conditions than systems at the front. Even minuscule differences could accumulate over decades of travel, requiring advanced synchronization technologies. The crew itself may experience subtle desynchronization, particularly in scenarios where artificial gravity or localized time pockets are created for psychological stability. Ensuring that life support systems, medical facilities, and data processing remain consistent becomes a top priority. One often overlooked consequence of time dilation is its impact on celestial navigation. Stars do not remain stationary in the universe. Over the course of decades or centuries, their positions shift significantly due to galactic drift. By the time travelers reach a distant star, the entire stellar neighborhood may have changed, with planets potentially shifting or disappearing from predicted locations. Advanced star maps must dynamically update as the mission progresses, relying on real-time observations rather than preloaded data. Artificial intelligence could play a crucial role here, making rapid adjustments to account for unexpected star movement. For travelers, time dilation introduces a profound social disconnect. Decades or centuries may pass on Earth, while only a few years elapse for the crew. Upon returning, they may find their loved ones aged or society entirely transformed. This temporal isolation is not just a logistical challenge, but an emotional one, shaping how future explorers approach interstellar missions. This disconnect also affects the exchange of knowledge. Scientific advancements on Earth might outpace the crew's understanding during their journey, leaving them reliant on pre-mission knowledge. Bridging this gap will require adaptive learning systems capable of updating the crew with compressed summaries of Earth's progress. Travelers nearing the speed of light may witness phenomena that Earth-bound astronomers can only simulate. Galactic collisions, supernovae, and even the formation of new stars could unfold within the observable time frame of their journey. This unique vantage point offers an unparalleled opportunity for scientific discovery, but complicates the interpretation of such events due to relativistic distortions. Astronomers on Earth may have captured the first phases of a supernova hundreds of years ago, and the crew may be able to see them unfold. To put these conflicting dates in context, we need sophisticated computer models that can place observations within the larger cosmic background. Time dilation also introduces ethical considerations. Sending humans on missions where they experience decades of isolation or return to an unrecognizable Earth raises questions about the psychological toll on explorers. Should humanity prioritize robotic probes for interstellar exploration, reserving human travel for scenarios where time dilation's effects are less extreme? Or does the potential for discovery outweigh these concerns? Additionally, travelers returning to Earth after centuries might face unique challenges in reintegrating into society. They could bring knowledge and experiences that seem alien to those who never left. Preparing for these eventualities will be as important as the journey itself. For travelers, the universe becomes a dynamic, ever-changing tapestry, revealing secrets hidden by the slower passage of time on Earth. This experience reshapes how humanity views its place in the cosmos, emphasizing the interconnectedness of space, time, and the human drive to explore. Revolutionary propulsion systems. Revolutionary propulsion systems are crucial for bridging the vast distances between stars. Traditional chemical rockets, though remarkable in their own right, are entirely inadequate for interstellar travel. They lack both the speed and efficiency needed to reach even our closest neighboring stars within a human lifetime. To meet this challenge, scientists and engineers are exploring propulsion methods that push the boundaries of our understanding of physics and engineering. Each system offers unique solutions and challenges, promising a glimpse into the future of interstellar exploration. One of the simplest yet promising concepts is the solar sail, which uses photons from the sun or a laser to push a spacecraft forward. Photons, while massless, have momentum. When they strike the reflective surface of a solar sail, they transfer this momentum, creating thrust. Unlike rockets that carry finite fuel, solar sails rely on external energy sources, making them lightweight and capable of continuous acceleration. The concept has been tested in missions like LightSail 2, and scaling it up could enable spacecraft to reach significant fractions of light speed. Building on this idea, laser-powered solar sails take the concept further. By using Earth-based or space-based lasers to direct intense beams of light onto the sail, propulsion becomes more controllable and powerful. These directed energy systems could allow a spacecraft to achieve extraordinary speeds. Projects like Breakthrough Starshot aim to use this technology to send small probes to Proxima Centauri within a few decades. The challenge, however, lies in developing sufficiently powerful lasers and ensuring precise aim over light years. Using solar wind or interstellar plasma interacting magnetic sails is another novel option. In order to create propulsion, these sails employ magnetic fields to redirect charged particles. One benefit of using magnetic sails for space travel is that they can operate in areas with low solar radiation. A two-in-one solution for lengthy missions, they may also protect from radiation. For higher thrust and sustained acceleration, scientists are looking to the fusion drives, which harness the power of nuclear fusion. Fusion, the process powering stars, produces immense energy by fusing light atomic nuclei like hydrogen or helium. A spacecraft equipped with a fusion drive could expel high-speed plasma, creating significant thrust. The challenge lies in achieving controlled fusion reactions. Current experiments like ITER focus on fusion for energy production, but adapting this for propulsion would require breakthroughs in containment and efficiency. Among fusion fuels, helium-3 stands out for its potential. Found in abundance on the Moon and gas giants, helium-3 could power fusion drives with minimal radioactive byproducts. Mining helium-3 might seem futuristic, but it aligns with the broader goals of space exploration. This clean and powerful fuel source could make fusion propulsion a practical reality in the coming decades. If fusion represents a near-future possibility, antimatter engines are the ultimate propulsion system. Antimatter annihilation releases energy with near-perfect efficiency, far surpassing any other known energy source. Just a few grams of antimatter could theoretically propel a spacecraft to significant fractions of light speed. However, producing and storing antimatter are monumental challenges. Current antimatter production is minuscule and energy-intensive, and storage requires advanced magnetic or electric traps to prevent annihilation with normal matter. A more experimental approach to fusion involves muon-catalyzed fusion, which uses muons to reduce the energy barriers for fusion reactions. This method could allow fusion to occur at lower temperatures and pressures, making it more practical for space propulsion. While still in its infancy, muon-catalyzed fusion represents an exciting avenue for overcoming traditional fusion's technical hurdles. For spacecraft that can rely on external energy sources, beam-powered propulsion systems offer a compelling solution. These systems use space-based laser or microwave arrays to transfer energy to a spacecraft, eliminating the need for onboard fuel. By reducing the spacecraft's mass, beam-powered propulsion can achieve higher speeds with less energy. However, this approach requires extensive infrastructure, including large-scale energy arrays and precise tracking systems. Nuclear thermal rockets are another practical option. These rockets superheat hydrogen and other propellants using nuclear reactors. Producing thrust, the gas is ejected at high speeds after being heated. An improvement over chemical rockets, nuclear thermal rockets have the potential to pave the way for ever more sophisticated propulsion technologies. Electric propulsion systems like ion drives and Hall thrusters offer exceptional efficiency for deep space missions. These systems work by expelling charged particles at extremely high speeds, producing low but steady thrust. While not suitable for escaping Earth's gravity, electric propulsion is ideal for interplanetary and interstellar travel, where long-term acceleration can accumulate significant velocity. The Bussard ramjet is among the most audacious plans. It would use enormous magnetic fields to pull hydrogen out of the interstellar medium. The gathered hydrogen would then power fusion processes, allowing for constant propulsion. Although the idea eliminates the need to transport fuel, it encounters obstacles such as the limited supply of interstellar hydrogen and the massive magnetic fields that would be necessary. For smaller missions, photonic thrusters represent an intriguing option. These systems use photons, such as those emitted by lasers, to generate thrust. While the force produced is minimal, photonic thrusters are highly efficient and could be used for lightweight probes traveling at high speeds. The concept of a relativistic propulsion introduces challenges unique to near light speed travel. At such speeds, the energy required for further acceleration grows exponentially, and even tiny particles can cause catastrophic damage due to their high relative velocity. Designing propulsion systems that can handle these conditions is a critical area of research. Hybrid propulsion systems offer a practical way to combine the strengths of different technologies. For example, a spacecraft could use solar sails for initial acceleration and switch to fusion drives for sustained thrust. Such an approach maximizes efficiency and adaptability, ensuring that the mission can handle a variety of conditions. Using quantum vacuum fluctuations for electromagnetic propulsion is another state-of-the-art concept. Scientists are aiming to create space-time-based propulsion systems by using quantum phenomena like the Casimir effect. Despite its theoretical nature, this research expands our knowledge of propulsion. Plasma-based propulsion, which uses magnetohydrodynamics to control charged particle flows, offers another promising avenue. Plasma thrusters can achieve high speeds and efficiency, making them suitable for interstellar missions. Advances in plasma physics are steadily bringing this technology closer to practical implementation. For extended missions, self-sustaining propulsion systems could collect propellant during flight. Concepts like self-regenerating hydrogen collection systems propose harvesting interstellar hydrogen or other materials as the spacecraft travels, reducing initial launch mass and ensuring continuous operation. The use of advanced propulsion systems could also address human health issues during long missions. For example, fusion-powered propulsion systems might create artificial gravity by accelerating in a way that mimics gravitational pull, reducing the physical toll of microgravity on human crews. One last option for tiny spacecraft propulsion is laser ablation propulsion, which is both accurate and lightweight. The spaceship generates propulsion by vaporizing materials on its surface using laser light. When dealing with missions on the micro or nanoscale, where conventional propulsion systems would be inefficient, this approach shines. Revolutionary propulsion systems represent humanity's best chance at reaching the nearest stars. From harnessing the power of photons to exploring the quantum vacuum, each system brings us closer to breaking free from the confines of our solar system. Navigating interstellar space. Navigating interstellar space presents challenges and opportunities that push our understanding of science and technology to its limits. Unlike terrestrial or even interplanetary travel, interstellar navigation requires precise systems capable of functioning autonomously for decades, if not centuries. This journey through the cosmic ocean is filled with challenges, from micrometeoroids to ever-shifting star positions. Each of these elements must be addressed to ensure the success of future missions. Pulsars, the remnants of massive stars that have exploded as supernovae, emit highly regular radio pulses. These pulses serve as natural beacons, allowing spacecraft to triangulate their position in space. Similar to how sailors use the stars to navigate Earth's oceans, pulsars act as a kind of galactic GPS, offering precision down to a millisecond. However, even pulsars aren't foolproof. Occasional glitches or irregularities in their signals require onboard systems to be prepared to recalibrate. At interstellar distances, the movement of celestial bodies becomes another critical consideration. Stars aren't stationary. They move through the galaxy at varying speeds and trajectories. Over the course of a long mission, the position of the destination star can shift significantly. This requires extremely accurate maps of stellar positions and motions. Current 3D star catalogues, like those produced by the Gaia Space Observatory, are crucial tools. These catalogues track the position and velocity of billions of stars, allowing scientists to predict their future locations with remarkable accuracy. But predicting star movements is just one part of the puzzle. The spacecraft itself must remain on course while dealing with various hazards and environmental factors. One such challenge is the interstellar medium, the sparse collection of gas, dust, and charged particles that exist between stars. While the interstellar medium is relatively empty compared to planetary atmospheres, its density varies. High-density regions can create drag on the spacecraft, slowing it down and potentially damaging sensitive instruments. Advanced sensors will be required to map the interstellar medium in real time, enabling the spacecraft to avoid dense regions. Micrometeoroids pose another danger. These tiny high-speed particles might seem insignificant, but at velocities close to light speed, even a grain of dust can cause catastrophic damage. Designing spacecraft with impact-resistant materials is one solution, but navigation systems must also be capable of detecting micrometeoroid-dense regions and altering course accordingly. For this, artificial intelligence will play a crucial role. AI systems can process vast amounts of data in real time, identifying potential hazards and making course adjustments faster than human operators on Earth ever could. Even without external hazards, maintaining precise navigation over interstellar distances is no small feat. Inertial navigation systems, which rely on gyroscopes and accelerometers to measure a spacecraft's orientation and velocity, will be essential. These systems allow the spacecraft to stay on course even when out of communication with Earth. However, inertial systems alone aren't enough. Over time, small errors in measurements can accumulate, leading to significant deviations. This is where pulsar navigation and star catalogues come back into play, providing reference points to correct these errors. Interestingly, the very act of traveling at near light speeds introduces new challenges. At such high velocities, relativistic effects become significant. Time dilation means that time on the spacecraft moves slower relative to Earth, affecting synchronization between onboard clocks and those on the ground. Additionally, the Doppler effect alters the frequency of signals sent between the spacecraft and Earth, complicating communication and navigation. Advanced algorithms will be needed to account for these effects, ensuring that data remains accurate. Using quasars, which are faraway objects that are incredibly brilliant and fueled by supermassive black holes, is another novel way to navigate. Because of their immense distance, quasars seem to maintain nearly constant relative locations across time, in contrast to pulsars. Because of this, they serve as great landmarks for future navigation, especially on missions that go much beyond our immediate stellar neighborhood. Energy efficiency is another factor that cannot be overlooked. Interstellar missions require careful trajectory planning to minimize energy consumption while maintaining speed and safety. For example, using gravitational assists from nearby stars or planets can help reduce fuel usage. However, this technique requires precise calculations and navigation to ensure the spacecraft doesn't veer off course. One of the most fascinating aspects of interstellar navigation is the potential use of cosmic background radiation as a navigational aid. The cosmic microwave background, CMB, is the faint afterglow of the Big Bang, permeating the universe. Variations in the CMB's intensity could theoretically be used to determine a spacecraft's position on large cosmic scales, though this remains a largely speculative idea. To navigate interstellar space effectively, redundancy is key. No single system can guarantee success over the decades or centuries required for a mission to reach even the nearest stars. Combining multiple methods, pulsar navigation, inertial systems, star catalogues, and more ensures that even if one system fails, the mission can continue. Redundancy also extends to the physical hardware. Backup systems for propulsion, communication, and navigation must be included to account for unexpected failures. As humanity looks toward the stars, there's also a growing interest in leaving navigational markers in interstellar space. These markers, or signposts, could serve as waypoints for future missions, creating a kind of cosmic highway system. Over time, such a system could turn interstellar travel from an isolated endeavor into a routine process, enabling exploration on a galactic scale. Navigating interstellar space is an extraordinary challenge, but each hurdle brings new opportunities for innovation. From leveraging pulsars and quasars as cosmic beacons to developing AI-driven course corrections, humanity's journey to the stars will be guided by ingenuity and determination. Overcoming communication delays. Overcoming communication delays in interstellar travel presents one of the most intricate challenges humanity must solve to successfully explore the nearest stars. Signals that travel at the speed of light, our fastest known method of communication, still take years to traverse the vast distances between Earth and even our closest neighboring stars. While our current systems handle planetary missions relatively well, interstellar distances introduce delays that push us to rethink our approach. This section delves into potential solutions and systems designed to bridge the immense communication gaps across light years. Communication across vast distances is naturally constrained by the finite speed of light. For instance, a signal from Earth to Proxima Centauri takes over 4 years to arrive, and another 4 years for the response to return. In practice, this means that a single exchange of data takes almost a decade. For comparison, communication with Mars, a challenge in its own right, takes between 4 and 24 minutes depending on planetary positions. These differences highlight just how fundamentally different interstellar communication challenges are. To manage these lags, spacecraft must become self-reliant, operating without constant input from mission control. Artificial intelligence systems will be critical. AI-driven decision-making processes allow spacecraft to adapt to unexpected conditions without waiting years for instructions from Earth. This autonomy requires the development of predictive models, where AI anticipates potential scenarios and executes pre-approved protocols. These systems must also learn to prioritize which data is sent back, ensuring critical information reaches us first, while less urgent data is stored for later transmission. Powerful laser-based communication systems offer a potential solution to the problem of signal deterioration. Lasers are able to offer very concentrated beams of light, which minimize signal attenuation in contrast to radio waves, which disperse as they travel. Although this approach necessitates accurate targeting and reliable equipment, it provides a practical means of sustaining communication across large distances. To demonstrate the approach's practicality, the Breakthrough Starshot program intends to launch tiny probes to Alpha Centauri and utilize lasers to transmit back to Earth. Despite their advantages, laser systems aren't immune to challenges. Interstellar dust, cosmic radiation, and other interference can distort signals. Dual wavelength transmissions, where signals are sent using multiple frequencies, help mitigate this problem by ensuring that at least one wavelength can penetrate the interference. Redundancy in data transmission, where the same data is sent multiple times, further increases reliability, reducing the chances of critical information being lost. Another innovative approach involves the development of interstellar relay networks. By strategically placing communication relay stations or satellites throughout the journey, we could create a chain of nodes capable of forwarding messages more quickly than direct transmissions. While this solution might seem futuristic, it mirrors strategies already used in planetary exploration, such as the Mars Relay Network. The concept could be scaled up for interstellar missions with the help of autonomous drones or mini-probes acting as intermediaries. Quantum communication is one of the most outlandish theories that has the potential to completely circumvent the speed of light. In quantum entanglement, two particles are connected in such a manner that any change to one of them is immediately mirrored in the other, no matter how far apart they are. On paper, this has the potential to enable real-time dialogue. Quantum experiments have made great strides recently, but real-world applications at interplanetary distances are still a ways off. This is more of a long-term solution than an instant prospect, due to the constraints of decoherence and the challenge of maintaining entanglement over huge distances. Another practical challenge is ensuring efficient data compression. When signals take years to travel, the amount of data sent must be optimized. Advanced algorithms can compress data without losing essential details, allowing spacecraft to transmit more information in fewer transmissions. Additionally, experiments need to be designed to generate clear, interpretable results that require minimal back-and-forth communication, reducing the dependency on constant updates from Earth. For example, a probe sent to explore exoplanets in the Alpha Centauri system might prioritize atmospheric scans and basic imaging over highly detailed spectroscopic analysis in its initial transmissions. This prioritization ensures that critical findings, such as potential biosignatures, are communicated first. Once the mission team on Earth analyzes these results, further instructions can be sent for more detailed investigations. Energy-efficient signaling is also a key concern for long-duration missions. Spacecraft traveling to distant stars must carry or generate enough power to maintain communication systems for decades or even centuries. Solar panels, commonly used in planetary missions, might become ineffective in the dim light of distant stars. Alternatives like onboard nuclear generators or advanced battery systems capable of recharging through kinetic or thermal energy must be explored. Interstellar space is filled with particles, radiation, and interference from other celestial phenomena, which can distort or drown out signals. Advanced error correction protocols will be essential to ensure that distorted signals are reconstructed accurately upon receipt. These systems, which are already in use for Earth-based communications, will need significant upgrades to handle interstellar conditions. The concept of predictive communication models also offers significant promise. By analyzing patterns in mission data and Earth-based expectations, spacecraft can prepare answers to anticipated questions before signals even reach them. This proactive communication strategy could significantly enhance mission efficiency, especially for experiments involving continuous observation, such as monitoring stellar activity or planetary orbits. However, overcoming delays isn't just a matter of technology. It's also about redefining mission goals to account for these delays. Long-term studies, such as observing the evolution of exoplanet climates or tracking changes in a star's magnetic field, are better suited for interstellar missions than tasks requiring constant back-and-forth instructions. This shift in focus allows missions to achieve meaningful results, despite the inherent communication challenges. Humanity must embrace the reality of signal time lags and integrate it into our exploration mindset. The sense of immediacy we've grown accustomed to in the digital age doesn't apply when dealing with interstellar distances. Instead, missions must prioritize resilience, patience, and autonomy. Whether through advancements in laser communication, AI autonomy, or speculative quantum methods, solving the communication delay problem will be as much about adaptability as it is about technology. Scientific objectives of interstellar missions. Understanding what makes interstellar missions so valuable means diving into the rich array of scientific objectives that drive these ambitious plans. It's not just about reaching the nearest stars, but about uncovering the secrets they and their planets might hold. The possibilities stretch across astrobiology, physics, and geology, offering insights that could redefine our understanding of the universe. Let's explore these objectives step by step, connecting each to the larger journey humanity is embarking on. When we think of distant stars, the question of life naturally arises. Identifying biosignatures goes beyond the classic focus on oxygen. Compounds like dimethyl sulfide or phosphine, gases produced by microbial life under specific conditions, could be just as significant. These trace elements provide a window into unique planetary environments, showing how diverse life might be outside Earth's template. For instance, phosphine detected in Venus's clouds raised debates about possible life processes, even in hostile conditions. Carrying that method into interstellar missions means using advanced spectroscopy to analyze exoplanet atmospheres from light years away, breaking down the chemical signatures they emit. Direct imaging is another key objective. With technology like coronagraphs and star shades, we can now block the glare of starlight to capture clear pictures of planets orbiting them. Imagine being able to distinguish oceans from continents or ice caps from deserts, giving us hints of habitability without landing a probe. This approach works hand in hand with atmospheric studies, where spectroscopy allows us to identify gases like methane and carbon dioxide, gases that could signal volcanic activity, geological shifts, or even the presence of life. But habitability is more than atmospheric composition. Planetary climate mapping takes this a step further by monitoring seasonal changes in temperatures or atmospheric circulation patterns. Observing such dynamics offers a glimpse into whether an exoplanet has a stable environment, a key factor for any ecosystem. While Earth's seasons depend on its axial tilt, understanding how alien climates function could reveal alternative systems shaping worlds far from our own. Turning our focus to the stars themselves, nearby systems like Alpha Centauri or Proxima Centauri present exciting opportunities for stellar studies. By examining stellar magnetic fields and radiation levels, we gain a clearer picture of how these forces influence orbiting planets. High-energy flares from a star, for instance, could strip a planet's atmosphere over time, rendering it barren. This insight helps us evaluate whether planets in similar conditions could sustain life or face insurmountable challenges. High-resolution surface mapping is another groundbreaking goal. Instead of just observing planets as dots of light, this method would provide detailed visuals of their landscapes. Are there rivers carving through rocky terrain? Could there be ancient impact craters or active volcanoes? These details offer clues about the geological history and potential for resources like water. For instance, if we find areas of frozen water on an exoplanet, it could signal past or present climates suitable for life. The discovery of liquid water is one of the most thrilling prospects in the search for exoplanets. The wavelengths that water absorbs may be determined by using thermal imaging and spectroscopy. Water is essential to all known forms of life. It is more than a chemical. Finding underground reservoirs or seas would be a huge deal for proving the existence of alien ecosystems. In the context of star systems, binary stars like Alpha Centauri A and B offer unique environments for study. Their gravitational interplay creates stable and unstable orbital zones for planets. Understanding how these interactions affect planet formation and stability is vital. It adds depth to our search for habitable worlds, showing how planets in such systems can be shaped by their dual star environments. The function of magnetic fields is another crucial component. The magnetic fields of planets like Earth serve to protect its inhabitants from the potentially dangerous rays of the Sun. It may be possible to ascertain whether an exoplanet possesses such safeguards by measuring the intensity of its magnetic field. The continual barrage of star winds would prove lethal to any kind of life, including microbes, if this natural barrier did not exist. Interstellar missions also open the door to studying objects that venture into planetary systems, like interstellar asteroids or comets. These visitors carry unique compositions that could provide clues about the conditions of their home systems. Sampling their material could shed light on how building blocks of life travel between stars. On a larger scale, missions could collect particles from the interstellar medium itself. This seemingly empty space is filled with traces of organic molecules, dust, and other particles. By analyzing these components, researchers could uncover how prebiotic chemistry, the kind that may lead to life, emerges in the harshest environments. Tidal forces add another dimension to our understanding of planetary dynamics. Planets orbiting close to their stars experience intense gravitational effects, stretching and heating their interiors. This process, known as tidal heating, can create conditions similar to Jupiter's moon Io, where geological activity thrives despite freezing outer temperatures. Moving beyond planets, Interstellar missions near young star systems allow us to witness the early stages of star and planetary formation. Observing these processes reveals how stars ignite and how planets coalesce from surrounding dust and gas. This knowledge builds on our understanding of our own solar system's formation billions of years ago. Another intriguing goal lies in studying photochemical reactions. When stellar radiation interacts with a planet's atmosphere, it triggers chemical changes. Over time, these reactions can create or destroy crucial molecules, shaping a planet's habitability. Monitoring these processes offers a deeper understanding of how atmospheres evolve. Beyond traditional studies, interstellar probes could even contribute to unraveling mysteries like dark energy or dark matter. Measuring gravitational effects in new environments or observing anomalies could yield breakthroughs in understanding these elusive forces that dominate the universe's mass and energy. Exoplanet spin and tilt studies also hold valuable insights. A planet's rotation rate and axial tilt influence its day-night cycles, seasons, and even weather patterns. Analyzing these properties helps paint a complete picture of how such planets function and whether they could host ecosystems similar to Earth's. As probes venture farther, they can capture high-energy events like gamma-ray bursts or supernovae in unprecedented detail. These rare phenomena shape galaxies by spreading heavy elements crucial for planet and star formation. Studying them provides clues about the broader processes of cosmic evolution. In the search for hidden secrets, advanced radar or seismic instruments could scan subsurface layers of planets and moons. Whether it's searching for underground oceans or revealing ancient geological structures, this approach goes beyond surface-level observations. Missions could test whether universal constants, like the speed of light or gravitational strength, remain consistent across different parts of the universe. Testing these constants in varying interstellar conditions helps validate or challenge foundational physics theories. These scientific objectives extend the promise of interstellar missions far beyond mere exploration. Each step, from detecting water to mapping geological histories. By unlocking these mysteries, humanity doesn't just explore, it grows. Building the interstellar probe. The process of building an interstellar probe is more than just constructing a spacecraft. It's about creating a machine that can withstand decades of travel through an unforgiving environment while performing advanced scientific tasks. Each component must function flawlessly and endure conditions that no human-made object has ever faced before. At the heart of this challenge is the balance between durability, efficiency, and adaptability. Miniaturization has become a cornerstone of modern technology, with nanotechnology playing a pivotal role. By shrinking systems without losing functionality, scientists can reduce the overall mass of the probe, which in turn decreases the energy required for propulsion. This compact design philosophy extends to scientific instruments, such as spectrometers and radiation detectors, ensuring that the probe can carry a comprehensive suite of tools without compromising its travel efficiency. Energy is another critical factor. For a mission that spans decades, a reliable and sustainable power source is essential. Solar arrays may work within a certain range of a star, but as the probe ventures farther, nuclear batteries or even fusion power systems become more viable options. Fusion, though not yet fully realized for space travel, offers a promising future by providing long-term energy with minimal fuel. Advanced energy storage systems, such as next-generation batteries, ensure that every watt is used efficiently. Once the probe is in interstellar space, it will face challenges unlike anything encountered within our solar system. Cosmic rays and high-energy particles pose a constant threat to the probe's electronics. To counter this, materials like graphene and specialized coatings are being developed for radiation shielding. These innovations not only protect the probe's systems, but also extend its operational lifespan, ensuring it can complete its mission without significant degradation. Heat management is another often overlooked aspect of spacecraft design. In the vacuum of space, heat generated by onboard electronics has nowhere to dissipate easily. Without proper thermal insulation and dissipation systems, critical components could overheat and fail. Engineers are designing radiative cooling mechanisms and advanced insulation to tackle this issue, ensuring the probe remains operational even under extreme conditions. The journey to another star is fraught with physical hazards. Micrometeoroids and interstellar dust, traveling at incredible speeds, can puncture or damage the probe. To address this, materials capable of withstanding high-speed impacts are being incorporated into the design. Additionally, some spacecraft concepts include self-healing materials, which can close small fractures or holes autonomously. This self-repair capability reduces the likelihood of catastrophic failure over long missions. Navigation is a major challenge for interstellar probes. Traditional methods used in our solar system become less effective when moving across light years. To navigate accurately, probes can use pulsars, distant, rapidly spinning neutron stars that emit precise radio pulses, as a kind of galactic GPS. By comparing the signals from multiple pulsars, the probe can determine its position in three-dimensional space with remarkable accuracy. Communication over interstellar distances requires innovation as well. The time delay for signals to travel back to Earth can span years, meaning the probe must operate autonomously most of the time. High-powered lasers are being considered for transmitting large amounts of data across these vast distances, offering a focused and efficient alternative to traditional radio waves. Compression algorithms and massive onboard storage systems will help manage the data collected during the journey, ensuring nothing is lost before it can be transmitted back to Earth. Autonomous decision-making is another necessity for a probe traveling to another star. The probe must be capable of responding to unexpected situations, such as avoiding obstacles or adjusting its course based on new data. Artificial intelligence systems are being designed to analyze conditions in real time, making critical decisions without human input. This level of independence not only ensures the success of the mission, but also reduces the need for constant oversight from Earth. Scientific exploration is the primary goal of interstellar probes, so their payload must include state-of-the-art instruments, from cameras capable of capturing high-resolution images of distant exoplanets to spectrometers analyzing their atmospheres. Every tool on board must contribute to understanding the target system. Some concepts even propose releasing small, detachable modules to study specific features of a star system, such as planetary surfaces or asteroid belts. The materials used in constructing the probe are as important as its systems. Radiation-resistant alloys, lightweight composites, and advanced ceramics are all being considered to build a spacecraft that is both durable and efficient. These materials not only protect against external hazards, but also contribute to the overall longevity of the mission, ensuring that the probe remains functional even after decades in space. Interstellar probes must also account for the unexpected. The interstellar medium, the matter and energy that exist between stars, is not uniform. Variations in density and composition could affect the probe's trajectory or systems. To adapt, onboard sensors must monitor these conditions continuously, and the probe must be capable of adjusting its course or operations as needed. One exciting area of development is the concept of modular probes. These spacecraft would be designed with expandable or replaceable sections, allowing future missions to send updates or enhancements to join the existing probe. This approach could extend the mission's capabilities, ensuring that the probe remains at the cutting edge of technology even decades after its launch. Cost is always a concern for missions of this magnitude. While advanced materials and systems offer incredible benefits, they come at a price. Engineers and scientists must balance innovation with affordability, finding ways to incorporate cutting-edge technology without exceeding budget constraints. Collaboration between nations and organizations may help distribute the financial burden while fostering innovation. The propulsion system is central to the probe's success. Solar sails, fusion drives, and antimatter engines are among the options being explored. Each has its strengths and challenges, but all require integration with the probe's overall design to maximize efficiency. For instance, a solar sail needs a lightweight frame to harness the gentle push of photons, while a fusion drive requires robust cooling systems to manage its intense heat output. Ultimate goal of an interstellar probe is not just to reach another star, but to return valuable data to humanity. Whether it's confirming the habitability of an exoplanet, mapping a star system, or analyzing the interstellar medium, every piece of information brings us closer to understanding our place in the universe. Building such a probe is a testament to human ingenuity, combining the best of science, engineering, and imagination into a single mission that could transform our knowledge. Timescales and multi-generational missions. When considering the enormity of interstellar travel, the timescales involved force us to think well beyond the boundaries of individual lifetimes. A journey to the nearest star systems may take decades, centuries, or even millennia. This timeline introduces unique challenges, opportunities, and ethical dilemmas that require innovative solutions to ensure the success of these monumental missions. Over the span of hundreds or thousands of years, celestial objects like stars, planets, and even interstellar clouds do not remain stationary. Gravitational forces from neighboring stars, galactic tides, and other phenomena gradually shift their positions. For an interstellar probe or generational ship, this movement is significant. It requires precise predictions using advanced models of stellar motion and gravitational influences. Current simulations already allow us to predict stellar drift for the next tens of thousands of years, but for extended missions, such projections must continually adapt, potentially guided by onboard AI recalibrating navigation in real time. Beyond movement, stars themselves evolve over time. The target system, such as Alpha Centauri, could undergo changes like increased stellar activity, solar flares, or variations in luminosity. These changes could affect the conditions of exoplanets within the system. While a planet might appear habitable today, it could experience drastic shifts in its environment by the time an interstellar craft arrives. Understanding this requires not just choosing the right targets, but also ensuring onboard equipment can monitor and adapt to unforeseen developments. For human-crewed missions lasting centuries, the concept of generational ships becomes essential. The initial crew may live out their lives on board, with successive generations taking their place. This raises the challenge of maintaining genetic diversity to avoid health problems related to inbreeding. Genomic planning could include cryogenically stored genetic material or technologies like cloning to introduce fresh genetic variability when necessary. These approaches would ensure long-term health and stability for onboard populations. On Earth, ecosystems recycle nutrients, water, and air seamlessly. Replicating this closed-loop functionality onboard spacecraft is crucial for sustaining life over long durations. Bioregenerative life support systems involve microorganisms, plants, and human beings, working together to maintain oxygen levels, recycle waste, and produce food. Advances in hydroponics, aquaponics, and synthetic biology could provide the tools needed to create compact, efficient ecosystems capable of functioning indefinitely. A journey lasting centuries would need to carry vast amounts of information, not only mission-critical data, but also the collective cultural knowledge of Earth. Quantum memory storage offers the potential for incredibly compact, radiation-resistant data storage. This would allow a spacecraft to preserve not only scientific knowledge, but also art, literature, music, and historical records, ensuring future generations on board remain connected to their origins. The vastness of space is not empty. Interstellar dust, micrometeoroids, and even unexpected gravitational anomalies pose risks to long-duration missions. Modern spacecraft design already includes shielding for micrometeoroid impacts, but for interstellar travel, self-healing materials using nanotechnology could offer an extra layer of protection. These materials might autonomously detect and repair microcracks or damage caused by high-speed particles. Generations born in space may develop new cultural norms, belief systems, or even languages distinct from those of their ancestors. The psychological impact of isolation and the absence of direct Earth connection could significantly influence the onboard society. Training and technology, such as virtual reality simulations of Earth environments, might help mitigate these effects. Additionally, AI companions could provide emotional support and maintain continuity of knowledge, acting as mentors and historians for successive generations. One alternative to maintaining generational crews is the development of hibernation or stasis technologies. By slowing metabolic processes, cryogenic systems could allow humans to survive for centuries in a dormant state. Research into natural antifreeze proteins found in Arctic organisms may offer insights into preserving biological tissue for long periods without damage. Artificial intelligence would likely play a central role in managing the complexities of a generational mission. From handling routine maintenance to resolving disputes among crew members, self-learning AI systems would act as the backbone of governance. These systems would need to be adaptive, capable of evolving alongside the society they help manage, ensuring relevance and effectiveness across centuries. Cosmic radiation poses a significant threat to both human health and spacecraft electronics. Prolonged exposure to high-energy particles can increase the risk of cancer, damage DNA, and degrade sensitive instruments. Magnetic shielding, similar to Earth's magnetosphere, could deflect these particles, while radiation-hardened materials might protect critical systems. Education would be critical for a mission lasting generations. Successive crews would need to learn complex technical skills, understand the mission's goals, and maintain the systems keeping them alive. AI tutors, holographic educators, and adaptive learning modules could ensure that each new generation is as capable as the last, maintaining mission continuity. If the destination includes a potentially habitable exoplanet, the journey itself could serve as an experimental phase for terraforming techniques. Controlled environments on board could simulate planetary atmospheres, testing methods to introduce oxygen, regulate temperatures, and develop sustainable biospheres. While the likelihood of encountering intelligent extraterrestrial life remains speculative, the ethical and practical considerations are immense. Should an interstellar mission encounter alien civilizations or ecosystems, protocols for peaceful interaction and observation without interference would be crucial. Pre-launch planning would need to consider these scenarios. During a long journey, the spacecraft might encounter asteroids or comets rich in useful materials like water, metals, or hydrogen. Developing systems to mine and utilize these resources could extend mission capabilities, reducing the need for large initial resource reserves. To conserve energy and maintain precise trajectories, interstellar spacecraft could utilize gravitational slingshot maneuvers around stars encountered en route. By harnessing the gravity of these massive objects, the spacecraft could adjust its velocity and direction with minimal energy expenditure. Exposure to low gravity, radiation, and the unique conditions of space travel could cause epigenetic changes, alterations in gene expression without changing DNA sequences. These changes might affect the health and behavior of successive generations. Monitoring and mitigating these effects would be vital for ensuring long-term mission success. Ethical concerns abound in a mission spanning lifetimes. The initial crew makes decisions that bind future generations, raising questions about consent and autonomy. Balancing the mission's goals with the well-being and freedom of those born into it would be a central ethical challenge. Maintaining mental health over centuries requires creating environments that simulate familiar Earth conditions. Artificial gravity, through rotational habitats, and controlled atmospheric lighting cycles could mimic the natural rhythms of Earth, providing psychological comfort. While the focus is often on reaching a destination, the possibility of returning to Earth or continuing to a second target should not be discounted. Ensuring that spacecraft have the capability to adjust goals mid-mission or return home could provide flexibility and security. Cosmic hazards on the journey. Navigating the vast stretches of interstellar space is an ambition that sparks imagination, yet it brings significant risks, many of which are rooted in the unforgiving nature of the cosmos. Among the most pressing challenges are the hazards that could confront a spacecraft traveling between the stars, from cosmic rays to the unpredictable interstellar medium. The journey to the nearest stars demands a robust understanding of these dangers and innovative approaches to overcome them. One of the most concerning threats comes from high-energy cosmic rays. These rays, consisting of atomic nuclei traveling at near-light speeds, can pierce through spacecraft shielding and interact with human cells, causing DNA damage. Over time, the cumulative exposure could lead to mutations or even serious health complications for any crew members on board. The spacecraft itself isn't immune. Electronics, critical for navigation and life support, can malfunction due to radiation exposure. Designing shielding to counteract these rays remains a priority, but it is a delicate balance. Heavier shielding provides better protection, but increases the spacecraft's mass, making propulsion more challenging. Paradoxically, shielding materials themselves can introduce secondary radiation hazards. When cosmic rays collide with certain metals, they produce secondary particles that can be as harmful as the original rays. This interaction demands careful selection of shielding materials, with researchers exploring composites like polyethylene, which generate fewer secondary particles than metals. Then there's the ever-present threat of micrometeoroids. These tiny particles, often no larger than grains of sand, travel at incredible speeds through space. At such velocities, even small particles can puncture spacecraft walls or erode their surfaces over time. Advanced impact-resistant materials, combined with deflective shielding, are being tested to address this issue. For unmanned missions, redundancy in critical systems ensures that a single impact won't compromise the entire spacecraft. However, for manned missions, the stakes are much higher, requiring a combination of real-time tracking systems and onboard repairs. Navigating through the electromagnetic radiation from stars adds another layer of complexity. X-rays, ultraviolet radiation, and intense solar winds can degrade spacecraft materials and damage sensitive instruments. Passing near active stars increases this exposure, forcing spacecraft designers to develop coatings and materials resistant to long-term radiation damage. Solar activity predictions also play a role in mission planning, ensuring that spacecraft avoid particularly hazardous regions during peak activity. The interstellar medium itself, once thought to be a near-perfect vacuum, is anything but empty. It contains a mixture of hydrogen atoms, interstellar dust, and plasma. While sparse, these particles can pose a problem when a spacecraft moves at high velocities. Hydrogen atoms, in particular, can create significant heat upon collision with a spacecraft traveling at relativistic speeds. This heating can damage the craft's surface and compromise sensitive instruments. Designing spacecraft to deflect or absorb this heat is an ongoing challenge. The variability in the interstellar medium's composition is another issue. Dense pockets of dust or molecular clouds can cause drag on the spacecraft or obstruct sensors used for navigation. Real-time adjustments will be critical, and autonomous systems must be sophisticated enough to adapt to these unpredictable conditions without human input. Charged particles within the plasma also interfere with electronic systems, emphasizing the need for electromagnetic shielding and robust system designs. Gravitational anomalies, such as those caused by rogue planets, black holes, or dense star clusters, can alter a spacecraft's trajectory unexpectedly. Detecting and accounting for these anomalies requires precise calculations and advanced navigation systems. Pulsars, which emit regular radio bursts, might serve as natural beacons to help spacecraft maintain their course, even when gravitational forces threaten to pull them off track. Even the spacecraft's propulsion system is at risk. Regions of the interstellar medium with higher than expected density or unexpected particle streams could interfere with ion drives or other advanced propulsion methods. Designers must build adaptability into propulsion systems to handle such variations. Relativistic speeds, the realm in which interstellar travel operates, introduce another challenge. At these velocities, detecting and reacting to hazards becomes increasingly difficult. Spacecraft traveling close to light speed have limited time to identify and avoid objects. Predictive algorithms paired with onboard AI will need to analyze potential threats and adjust trajectories instantaneously. Human oversight, while essential for long-term mission management, will be insufficient for split-second decisions. An often overlooked hazard comes from the spacecraft's prolonged exposure to temperature extremes. Spacecraft pass through regions where temperatures fluctuate dramatically, depending on proximity to stars or other energetic phenomena. Thermal management systems must maintain internal conditions, ensuring the safety of equipment and, in manned missions, the crew. Magnetic fields in interstellar space, although weaker than those found near planets, can still pose challenges. Large-scale interstellar magnetic fields can disrupt onboard instruments and navigation systems. Additionally, as spacecraft move through plasma, they can accumulate static charges, potentially damaging sensitive electronics if not properly grounded. One particularly catastrophic, though rare hazard is a gamma-ray burst, GRB. These bursts, caused by events like the collapse of massive stars or the merger of neutron stars, release immense energy in a focused beam. A spacecraft caught within the range of a GRB could face total destruction. While the likelihood of encountering such an event during a mission is low, the potential impact underscores the need for contingency planning. In addition to these physical threats, the unknowns of interstellar space present psychological and logistical challenges. For manned missions, the isolation and long-duration exposure to low gravity could weaken the crew's physical and mental resilience. Combining rigorous pre-mission training with onboard support systems may mitigate some of these effects. Cosmic hazards are not insurmountable, but they highlight the complexity of interstellar travel. Mitigating these risks will require a blend of cutting-edge technology, robust mission planning, and the ingenuity of human and AI collaboration. From designing advanced radiation shielding to developing adaptive propulsion systems, humanity's journey to the stars demands preparation for a universe that is as unpredictable as it is vast. Ethical and philosophical dimensions. The quest for interstellar travel pushes humanity to confront questions that go beyond technology and physics. It leads us to consider how our actions in the universe reflect on our values and responsibilities. This segment explores the moral dilemmas and philosophical questions that accompany the journey to the stars. When discussing interstellar missions, one of the most critical considerations is the potential impact on alien ecosystems. Suppose a habitable exoplanet is discovered. How can we ensure that humanity's presence doesn't disrupt or destroy delicate life forms or environmental balances? The history of colonization on Earth serves as a stark warning, showing how ecosystems can be irrevocably altered by new arrivals. Scientists and ethicists suggest adopting strict planetary protection protocols, ensuring that even unintentional contamination from microbes does not occur. If intelligent extraterrestrial life is discovered, humanity must decide how to engage responsibly. What rights should these beings have? How do we respect their autonomy without imposing human-centric ideals? International organizations and space agencies have only scratched the surface of preparing guidelines for such encounters. Yet the stakes are enormous. Miscommunication or an aggressive stance could lead to catastrophic outcomes. Ethical frameworks must prioritize cooperation and mutual respect, drawing from lessons in diplomacy and cross-cultural interactions here on Earth. Exploration often brings questions of ownership. If a planet rich in resources is found, who gets to claim it? Is it the nation or organization that funded the mission, or should these resources belong to all of humanity? Some argue that interstellar resources should be treated like international waters, owned by no one and shared by all. Others worry about how enforcing such ideals in a distant star system could be practical. Without clear agreements, conflicts may arise, echoing Earth's history of territorial disputes. Investing in interstellar exploration raises difficult questions about priorities. Critics argue that the resources dedicated to reaching the stars could address pressing issues like poverty, inequality, and climate change on Earth. Supporters counter that space exploration fosters innovation, unity, and long-term survival. The challenge lies in balancing these needs, ensuring humanity doesn't neglect its home planet while reaching for the cosmos. The desire to explore can unintentionally mirror darker aspects of history, such as imperialism and exploitation. There is a risk that interstellar missions could adopt an extractive mindset, treating discovered worlds as mere resources to be consumed. Preventing this requires careful planning, transparency, and international oversight. Ethical exploration must prioritize respect for potential extraterrestrial environments and life forms, no matter how simple or unfamiliar they may be. If humanity discovers that we are truly alone in the universe, the implications could be profound. Such knowledge might inspire a renewed focus on protecting Earth as the only cradle of life, or it might evoke existential despair. Conversely, finding life could spark equally significant questions. How do we relate to these beings? Should we strive for unity or accept isolation? These are not just scientific questions, but deeply human ones. Long-duration missions to other star systems will bring challenges for the people involved. What rights do crew members have during multi-decade or multi-generational journeys? How do we ensure their mental well-being, especially if they are born into a mission they didn't choose? The ethics of autonomy, fairness, and mental health take on new dimensions when lives are spent in confined, high-stakes environments far from home. Interstellar missions risk reducing human culture to a single narrative or dominant worldview. This could marginalize certain traditions, languages, or philosophies. Designing missions that include diverse perspectives is essential, not only for fairness, but also for creating a holistic legacy of humanity. It's about showing that exploration reflects the richness of our collective identities. The unintentional introduction of Earth-based species to extraterrestrial ecosystems is a major concern when it comes to interstellar travel. Following in the footsteps of invading species on Earth, this cross-contamination has the potential to severely damage native ecosystems. Spacecraft sterilization and tight controls to prevent the transfer of any biological material from Earth to other planets are necessary to avoid this. The drive to explore is deeply embedded in human history. Some argue that this curiosity is justification enough for interstellar travel, while others see it as an excuse for unchecked expansion. Philosophers have debated whether humanity's ambition is an act of arrogance or a natural response to the unknown. Regardless, this desire to push boundaries defines who we are as a species. Even if interstellar travel fails to establish human colonies, the act of exploration ensures the survival of our knowledge. By sending data, history, and art into space, humanity creates a legacy that may endure even if Earth does not. This immortality of culture and science is often cited as one of the most meaningful aspects of interstellar missions. The discovery of life, or the confirmation of its absence, could profoundly impact religious and spiritual beliefs. For some, the existence of extraterrestrial life might validate their faith, while for others, it could challenge core doctrines. Similarly, the vast emptiness of space could inspire awe and existential reflection, reshaping how humanity views its place in the universe. Given the risks of direct human involvement, artificial intelligence, AI, could play a critical role in interstellar missions. Machines might act as humanity's first representatives, exploring and even communicating on our behalf. This raises questions about whether AI can truly embody human values and ethics when interacting with alien civilizations. The technologies developed for interstellar travel, such as advanced propulsion or powerful AI, have dual-use potential. While they promise benefits for exploration, they could also be weaponized or misused on Earth. Managing these risks requires global agreements and ethical safeguards to ensure that advancements serve humanity's collective good. Interstellar exploration offers a unique opportunity for global unity. Instead of competing for dominance, nations could collaborate on missions, pooling resources and expertise. The Apollo program showed how shared goals inspire humanity, and interstellar missions could take this spirit to new heights. Such efforts might also address the ethical need for inclusivity, ensuring that exploration reflects the aspirations of all people, not just a select few. Self-replicating probes, designed to reproduce and spread across star systems, could exponentially accelerate exploration. However, these machines could spiral out of control, consuming resources indiscriminately. Ethical guidelines must address the potential risks of unleashing autonomous systems into the cosmos without adequate oversight. If humanity inadvertently causes harm to an alien ecosystem or species, what responsibilities do we have to make amends? The concept of cosmic justice pushes us to consider how to balance exploration with accountability. Whether through reparations, restoration efforts, or cessation of activity, humanity must prepare for the possibility of mistakes. As humanity reaches for the stars, the question of responsibility becomes ever more significant. Do we owe it to ourselves, our descendants, or the universe itself to explore? Or should we prioritize preserving what we already have? These questions remind us that interstellar travel is not just a technological challenge, but a profound ethical journey. This exploration of ethical and philosophical dimensions highlights how interstellar travel is as much about humanity's inner world as it is about the outer cosmos. Balancing ambition with responsibility, curiosity with caution. Shifting humanity's perspective. Space exploration and the dream of interstellar travel aren't just about crossing great distances or finding new planets. They're also about changing how humanity views itself. When we step back and look at Earth from the outside, it isn't just a planet, it's home. From the perspective of the stars, our boundaries, conflicts, and divisions seem small. The first time astronauts looked back at Earth from space, they described a sense of unity, a feeling that everything and everyone they knew existed on a fragile, glowing sphere. Interstellar travel takes that idea even further, forcing us to think not just about Earth, but our place in the cosmos. The vastness of space reminds us that Earth is unique. It's a delicate ecosystem in a universe that's mostly empty and hostile to life. Seeing Earth as a single, vulnerable entity inspires a deep respect for its resources and a sense of responsibility to protect it. This perspective pushes us to ask, what do we do with this gift of life? When viewed against the stars, the idea of harming our planet for short-term gains feels reckless. Space exploration helps us see that our survival depends on taking care of the only home we've ever known. The need for collaboration is another lesson space teaches us. Achieving interstellar travel isn't something one country or company can do alone. It requires the pooling of resources, knowledge, and ideas from across the globe. Working together to reach the stars helps break down barriers between nations. It shifts the focus from competing over land, resources, or power to working as one species for a common goal. This unity doesn't just benefit space exploration, it creates a model for solving problems on Earth. Thinking about interstellar travel changes how we see time. It's easy to think about projects in terms of years or decades, but when planning a journey to another star, we're talking about centuries. This challenges us to think about the future in a new way. What kind of world will the next generations inherit? Multi-generational missions teach us to plan for the long term, setting goals that won't be achieved in our lifetimes but will still matter to our descendants. The search for life in the universe is another way interstellar exploration expands our perspective. If we find even a trace of life elsewhere, it will be one of the greatest discoveries in history. It will prove that we are not alone and that life isn't unique to Earth. On the other hand, if we find that the universe is silent, it highlights just how rare and precious life here is. Either outcome changes how we think about ourselves and our place in the universe. Space doesn't just reveal humanity's vulnerability, it also shows our resilience. Life on Earth has survived countless challenges, from asteroid impacts to ice ages. The thought of life adapting and thriving in extreme environments, even on other planets, is a testament to its strength. As we look for signs of life elsewhere, we are reminded that adaptability is one of humanity's greatest strengths. Interstellar exploration forces us to grapple with big questions about ethics and responsibility. If we were to discover a habitable planet, what would be our duty to its environment? Should we preserve it as it is or adapt it for human use? These aren't just hypothetical questions. They're a test of how much we've learned about living in harmony with our surroundings. Colonizing a new world isn't just about survival. It's about learning to coexist with other ecosystems. The cultural impact of interstellar exploration is just as profound as its scientific achievements. Reaching for the stars inspires new ideas in art, literature, and philosophy. It gives people a sense of wonder and pushes them to imagine the unimaginable. The stories we tell about space shape how we see ourselves and what we believe we're capable of achieving. Success in space changes what we value. It redefines progress, moving away from economic or political achievements to milestones that advance humanity as a whole. A successful interstellar mission would be a triumph for all of humanity, reminding us that we're all part of the same journey. Interstellar travel connects us to the curiosity that's driven humans for millennia. Thousands of years ago, people looked up at the stars and wondered what was out there. Today, we have the technology to start answering those questions. This connection to our ancestors' curiosity reminds us that exploration is part of who we are. The same drive that led early humans to cross oceans now pushes us to cross galaxies. Thinking about the possibility of intelligent life elsewhere changes everything. If we find intelligent beings, it will raise new questions about communication, understanding, and coexistence. If we don't, it challenges us to reflect on the uniqueness of human consciousness. Either way, the search for intelligent life is a search for meaning. Space exploration also makes us rethink survival. On Earth, survival often means finding food, shelter, and security. In space, it means adapting to new environments, solving problems creatively, and working together. These lessons can help us deal with challenges here on Earth, too. Generational thinking is another shift brought on by space exploration. When we plan for missions that will take decades or centuries, we start to value the contributions of people who may not see the end results of their work. This shift teaches us patience and the importance of laying foundations for future generations. The immensity of space is humbling. It reminds us that we are just one species on one planet in one galaxy. This perspective doesn't diminish our importance, it highlights our shared destiny. It shows that despite our differences, we all face the same challenges and share the same future. Space exploration also brings ancient ideas back to life. For centuries, humans have created myths and stories about the stars. Modern science gives us new ways to explore those same mysteries, connecting us to a long tradition of stargazing and storytelling. Redirecting resources from conflict to exploration shows how space can inspire peace. The same technologies used to reach the stars can be used to solve problems on Earth. Interstellar exploration reminds us that innovation is a better use of resources than competition. The quest for the stars drives changes in education too. As we prepare for interstellar missions, we create new fields of study in science, engineering, and ethics. These advancements make education more dynamic and relevant, inspiring future generations to think beyond Earth. Perhaps the most profound shift comes from seeing Earth from the outside. It's easy to take life for granted when we're surrounded by it, but from space, Earth looks small, fragile, and full of possibilities. This perspective inspires hope. It shows that even in the face of immense challenges, humanity has the creativity and determination to reach for the stars. technological advancements, and spin-offs. Advancements made in the pursuit of interstellar travel do not just serve space exploration. They ripple through industries on Earth, creating transformative innovations. These breakthroughs go beyond the usual frontiers of technology, touching material science, energy efficiency, AI development, and even our understanding of human biology. To create spacecraft capable of surviving interstellar conditions, engineers have pushed the limits of materials science. Ultralight yet durable materials like graphene and carbon nanotubes have emerged, providing unprecedented strength while minimizing weight. These advancements are not limited to spacecraft. Their impact extends to infrastructure projects, including earthquake-resistant buildings and lightweight, fuel-efficient vehicles. Self-healing materials, which can autonomously repair minor damages, are another byproduct. Originally designed to extend spacecraft lifespans, these materials are finding applications in consumer electronics and even clothing, promising products that last longer with minimal maintenance. Interstellar probes demand highly autonomous systems, as real-time human intervention becomes impossible over vast distances. This necessity has driven innovations in AI, particularly in machine learning and decision-making algorithms. These advancements have immediate Earthbound applications. For instance, AI models trained for interstellar problem-solving are now being adapted for disaster response, medical diagnostics, and even traffic management. The ability of AI to process vast amounts of data and make autonomous decisions under unpredictable conditions represents a leap forward in multiple sectors. Propulsion systems for interstellar missions have spurred research into compact and efficient energy sources. Efforts to develop small-scale nuclear fusion reactors could revolutionize clean energy on Earth. Similarly, innovations in solar panel efficiency, driven by the need to power spacecraft in deep space, have improved renewable energy systems. Lightweight, high-output solar panels are now transforming the way we approach green energy solutions, from urban rooftops to remote, off-grid locations. The development of navigation systems capable of pinpoint accuracy across light years has immediate implications for terrestrial travel. Pulsar-based navigation, which uses the predictable timing of pulsars as a galactic GPS, could redefine Earth's navigation systems, offering precision independent of satellite networks. This technology is particularly valuable for maritime and aviation industries, where reliable navigation is critical in remote areas. These systems could also assist in rescue missions or during satellite outages, providing fail-safes for existing infrastructure. Interstellar missions require overcoming significant communication delays. While quantum entanglement remains theoretical for now, research into quantum communication has already laid the groundwork for secure, high-speed data transfer on Earth. Quantum encryption, developed for interstellar use, is now influencing cybersecurity systems. Meanwhile, high-powered lasers designed for deep space communication are being adapted for Earth-based data transmission, offering faster and more efficient internet connectivity. The constraints of interstellar travel, where every gram counts, have driven advancements in miniaturization. Nanoscale sensors and devices, initially intended for space probes, are being repurposed for medical diagnostics. These tiny devices can monitor patient health in real time, providing insights into conditions like heart disease or cancer. Similarly, compact electronics developed for space missions are influencing consumer electronics, leading to smaller, more powerful smartphones and wearable technologies. Interstellar propulsion systems, such as ion drives and solar sails, are influencing Earth-based transportation. Magnetic propulsion technologies, inspired by these systems, are being explored for high-speed trains. Such innovations could make travel faster and more sustainable, reducing reliance on fossil fuels. In aviation, concepts derived from spacecraft propulsion may lead to more efficient jet engines, cutting down emissions and operational costs. Shielding spacecraft from cosmic rays has driven advancements in radiation protection materials. These breakthroughs are now being used in medical fields, particularly in radiology and cancer treatment. Protective gear developed for astronauts is also being adapted for workers in nuclear power plants, ensuring safety in high radiation environments. Spacecraft designed for self-sustaining missions rely heavily on 3D printing technology. These printers allow for on-the-spot manufacturing of replacement parts, reducing dependency on resupply missions. On Earth, this technology is revolutionizing industries from construction to healthcare. For instance, 3D printing is enabling faster construction of affordable housing, and even the creation of prosthetics tailored to individual needs. Handling the vast data collected by interstellar missions has pushed the limits of data processing and storage technologies. These advances are directly influencing Earth-based applications, from big data analysis to cloud computing. Efficient data compression techniques are enabling faster transmission of information, while real-time data processing improves decision-making in industries like finance, healthcare, and environmental monitoring. Understanding the effects of long-term space travel on the human body has led to discoveries in treating health issues like muscle loss and bone density reduction. Closed-loop life support systems, designed to recycle air, water, and waste on spacecraft, are being adapted for sustainable agriculture and waste management on Earth. Such systems could provide solutions for resource-scarce environments, particularly in regions facing water shortages. Interstellar missions require cooperation between nations, scientific institutions, and private companies. These collaborative frameworks are proving invaluable for addressing global challenges. The teamwork model established by interstellar projects is being used to combat climate change and tackle pandemics, showing how shared goals can unite diverse groups for the greater good. Ultra-high-resolution imaging tools, developed to study distant exoplanets, are now being used in medical diagnostics and environmental monitoring. Spectroscopic techniques, which identify the composition of alien atmospheres, are enhancing Earth-based applications, from food safety to pollution tracking. The allure of space exploration drives interest in STEM fields, inspiring a new generation of scientists and engineers. Educational programs linked to interstellar projects help foster innovation across industries. By encouraging curiosity and critical thinking, these initiatives ensure that advancements in space exploration ripple through society. Robots designed to operate autonomously in extreme space environments are influencing other sectors. For example, deep-sea exploration and mining are benefiting from robotics developed for interstellar missions. Telerobotic technologies also have applications in telemedicine, allowing surgeons to operate remotely with precision tools. Water recycling systems developed for spacecraft have direct implications for Earth's water crisis. These systems are being deployed in areas where clean water is scarce, offering solutions for disaster relief and sustainable living. Innovations in minimizing resource consumption in space missions also influence sustainable practices on Earth. AI systems trained to analyze interstellar data are being adapted for Earthbound applications. From genomics to weather prediction, these systems are accelerating research and improving accuracy. Automated monitoring systems developed for space environments are now being used to predict and manage natural disasters. The pursuit of interstellar exploration is not just about science. It's about inspiring humanity to think beyond immediate boundaries. The shared goal of reaching the stars fosters innovation and pushes society to address challenges with renewed focus. Public enthusiasm for space exploration leads to funding and attention for technologies that benefit daily life, ensuring the far-reaching impact of these advancements. Materials that adapt to extreme conditions in space, such as shape memory alloys, are finding uses in fields ranging from surgery to construction. These innovations promise more efficient tools and resilient infrastructure, improving lives in unexpected ways. The end goals of exploration. The journey toward the stars is not just about reaching distant systems. It's about unlocking answers to humanity's biggest questions and securing a long-term future. By exploring the farthest reaches of the universe, we expand the boundaries of what it means to exist, innovate, and connect as a species. One of the core goals of interstellar exploration is to ensure humanity's survival. Earth, though vibrant and full of life, is vulnerable to cosmic and planetary threats. Massive asteroid impacts, supervolcanic eruptions, or even runaway climate change could jeopardize life on this planet. Establishing off-world colonies can provide humanity with a backup plan, ensuring that even if one disaster befalls Earth, the species continues to thrive elsewhere. Colonies on exoplanets like Proxima Centauri b, or those yet to be discovered, would act as safe havens. By diversifying where humanity exists, we protect ourselves from a single point of failure. It's a strategy nature itself uses, spreading seeds far and wide to ensure survival even in harsh conditions. Another objective is to deepen our understanding of how the universe began and evolved. By studying the stars, galaxies, and interstellar matter, we gain critical insights into cosmic phenomena that remain mysteries. Observations from distant star systems allow us to refine theories about the Big Bang and the nature of dark matter and energy. Interstellar probes equipped with advanced sensors could analyze black holes, pulsars, and nebulae at close range. Such missions could reveal processes that we can't observe from Earth. Understanding these forces helps us connect the dots of how the universe shaped itself into the dynamic and complex system we see today. The question of whether we are alone in the universe is one of the most profound. Interstellar missions aim to identify biosignatures, chemical markers like methane, oxygen, and water vapor that indicate the presence of life. These missions focus on exoplanets within the habitable zone of their stars, where conditions might allow liquid water to exist. Finding microbial or even intelligent life would redefine humanity's place in the cosmos. It would challenge our philosophies, religions, and perspectives. The discovery of alien ecosystems could even provide clues about how life began on Earth, helping us better understand the conditions that spark biological processes. Interstellar exploration is a gateway to unparalleled scientific advancements. The space between stars, filled with interstellar medium, is unlike any environment we've studied before. Investigating phenomena like plasma waves, cosmic rays, and interstellar clouds helps refine our understanding of matter and energy. Probes traveling through these regions would serve as laboratories, testing physical theories in conditions impossible to replicate on Earth. By pushing the boundaries of knowledge, interstellar missions pave the way for discoveries that reshape our understanding of physics and chemistry. The challenges of interstellar travel drive innovation. Developing propulsion systems capable of near-light speeds requires breakthroughs in energy generation, storage, and management. Solar sails, fusion drives, and antimatter engines are just the beginning of what's needed for interstellar missions. These technologies often find applications on Earth. Advanced materials developed for space probes, for example, could lead to more efficient energy systems or durable structures. The pursuit of the stars accelerates innovation in ways that benefit humanity across industries. Colonizing other worlds is more than a survival strategy. It's about ensuring humanity thrives as a cosmic species. While some planets may require terraforming, altering their atmosphere and surface to make them habitable, others might already have the conditions for life. Spreading humanity across star systems reduces the dependence on Earth. It opens the door to building diverse societies that adapt to their environments, creating a richer tapestry of human culture and experience. Interstellar exploration offers a new perspective on Earth. Observing alien worlds highlights the uniqueness of our planet's biosphere, from its breathable atmosphere to its vast oceans. This perspective fosters a deeper appreciation for Earth's ecosystems and the urgent need to protect them. The comparison also encourages environmental responsibility. As we discover how rare Earth-like conditions might be, the motivation to preserve our home planet intensifies. The vastness of space holds untapped resources. Asteroids, planets, and moons contain materials like rare metals, water ice, and helium-3. Interstellar missions could identify resources that become the foundation of off-world economies. Harvesting these resources has the potential to revolutionize industries on Earth, providing materials for technology, construction, and energy production. It also sets the stage for building self-sustaining colonies that don't rely on Earth's limited reserves. The journey to the stars is a test of endurance. Human physiology faces challenges like radiation exposure, muscle atrophy, and isolation. Research into these effects leads to advancements in medicine, nutrition, and psychology. Machines also play a critical role. Robotic systems and AI need to operate autonomously for decades, adapting to unforeseen challenges. The lessons learned from these systems feed back into Earth-based robotics, enhancing everything from healthcare to disaster response. Interstellar missions confront humanity with profound questions. Why do we explore? What does it mean to expand beyond Earth? These questions don't have simple answers, but the journey itself is an act of discovery. Exploring the stars prompts us to consider our purpose as a species. Are we driven by curiosity, survival, or a desire to leave a legacy? The pursuit of the stars is as much a philosophical journey as it is a scientific one. Colonizing other star systems provides opportunities for experimentation. Distant colonies could develop unique cultures, governance systems, and economies independent of Earth's constraints. These societies might explore alternative ways of living and organizing themselves. This diversity enriches humanity as a whole. It demonstrates adaptability and resilience, qualities essential for surviving in the cosmos. Interstellar missions require global collaboration. No single nation has the resources or expertise to achieve such ambitious goals alone. The shared pursuit of the stars fosters international partnerships and peaceful cooperation. History shows that major scientific endeavors, like the International Space Station, bring nations together. Interstellar exploration takes this unity to a cosmic scale, demonstrating humanity's ability to work collectively for a greater purpose. Charting the unknown is a fundamental part of exploration. Interstellar missions aim to create detailed maps of space, identifying habitable zones, resource-rich regions, and navigational hazards. These maps serve as guides for future missions, expanding humanity's reach. Such mapping also helps scientists understand the structure of the galaxy, from spiral arms to star clusters. It's a step toward unlocking the secrets of the Milky Way. Distant star systems may hold clues to new energy sources. Concepts like Dyson spheres, structures that harvest a star's entire energy output, could revolutionize power generation. Exploring other systems also tests the feasibility of fusion reactors and antimatter production. These advancements not only support space exploration, but also address Earth's growing energy demands. The pursuit of interstellar travel drives progress towards sustainable energy solutions. Interstellar missions are just the beginning. As humanity masters travel within the Milky Way, the next step is reaching other galaxies. The technology and knowledge gained from early missions lay the foundation for intergalactic exploration. Such endeavors are a testament to humanity's determination. They push the boundaries of what's possible, inspiring future generations to dream even bigger. Venturing into space redefines what it means to be human. No longer confined to one planet, humanity becomes a cosmic species. This shift in identity influences how we view ourselves and our place in the universe. Interstellar exploration challenges us to adapt, innovate, and unite. It's a journey that reshapes humanity, not just technologically, but also culturally and spiritually. Preserving human achievements across the stars ensures our legacy endures. Art, music, literature, and science could be shared with alien civilizations or serve as a record for future humans. Interstellar travel immortalizes human creativity and knowledge. Speculations on leaving the Milky Way. Leaving the Milky Way is a task that stretches our understanding of science and technology to its absolute limits. Moving beyond the galaxy is not just a matter of distance. It is about tackling challenges that grow exponentially with each light year traveled. The Andromeda Galaxy, our closest large neighbor, is 2.5 million light-years away, a distance that makes even interstellar travel seem manageable by comparison. Let's delve into the intricate layers of challenges and possibilities that this endeavor brings. Distances between galaxies are mind-bending. Moving from one star to another within our galaxy is already daunting, but crossing the space between galaxies elevates the difficulty to a cosmic scale. The concept of a light year, while helpful for interstellar distances, becomes almost meaningless when dealing with millions of light years. Even traveling at the speed of light, reaching Andromeda would take millions of years. This underscores the need for technologies that go far beyond what we currently envision for interstellar travel. The energy required for intergalactic travel surpasses anything humanity has ever imagined. Current propulsion systems, even futuristic ones like fusion or antimatter engines, are barely adequate for traveling to nearby stars. Moving to another galaxy would likely require breakthroughs in energy generation, such as harvesting energy from black holes or utilizing massive amounts of antimatter. Each of these energy sources presents its own scientific hurdles, from containment to scalability. Cosmic expansion adds another layer of complexity. Galaxies are not stationary. They move away from each other due to the universe's ongoing expansion. The farther a galaxy is, the faster it recedes. For nearby galaxies like Andromeda, gravitational forces counteract expansion, but for galaxies farther away, the effect becomes dominant. Over time, the distances to these galaxies grow larger, potentially making intergalactic travel an ever-receding goal. Interstellar space within the Milky Way is not empty, and neither is the intergalactic medium. The space between galaxies contains sparse particles of gas, dust, and even dark matter. Though thinly spread, these materials could pose challenges to spacecraft traveling at high speeds. Navigational systems must account for these hazards to prevent damage over prolonged journeys. Gravity assists, used effectively in interplanetary missions, could be extended to intergalactic travel. Massive galaxy clusters and supermassive black holes might act as slingshots, providing spacecraft with additional speed. These gravitational maneuvers would require precise calculations and long-term mission planning, but they could reduce the energy burden significantly. Wormholes remain a theoretical solution for intergalactic travel. If traversable wormholes exist, they could provide shortcuts through space-time, connecting distant points in the universe. However, creating or finding a stable wormhole would require advances in physics that we can barely comprehend today, including the manipulation of exotic matter to keep the passage open. Dark energy, the force driving the universe's expansion, could hold clues to intergalactic travel. If we could harness or counteract dark energy, it might allow us to bridge immense distances. Scientists are still in the early stages of understanding this enigmatic force, but its role in shaping the universe makes it a critical area of study for future explorers. The Milky Way's satellite galaxies, like the Magellanic Clouds, offer closer destinations for testing intergalactic technologies. These smaller galaxies could act as waypoints, allowing humanity to establish a foothold beyond our galaxy before attempting more ambitious journeys. Studying these satellites could also provide insights into the structure and dynamics of larger galaxies. Intergalactic travel requires solutions for survival over millions of years. Technologies like cryogenics could preserve human crews in suspended animation, while generational ships might allow successive generations to live and work aboard the spacecraft. Another possibility is uploading human consciousness into digital forms, bypassing the limitations of biological bodies altogether. Before embarking on physical journeys, humanity might detect signals from other galaxies. Advanced telescopes could pick up intergalactic radio waves or laser pulses, suggesting the presence of extraterrestrial civilizations. These signals could guide our exploration efforts, pointing us toward promising targets. Traveling at relativistic speeds creates time dilation, compressing time for the travelers but stretching it for observers back home. For an intergalactic journey, this effect becomes extreme. A crew might experience a manageable amount of time during their journey, but thousands or millions of years would pass on Earth. This creates profound challenges for maintaining relevance and communication. Carrying enough fuel and resources for an intergalactic journey is impractical. Spacecraft may need to extract hydrogen or other particles from the intergalactic medium to sustain themselves. This approach would require onboard systems capable of identifying and utilizing these sparse resources efficiently. Massive generational spacecraft or artificial worlds could house entire populations for intergalactic travel. These mobile habitats would need to be self-sufficient ecosystems capable of sustaining life indefinitely. They could serve as both transport vessels and new homes for humanity. Mapping the intergalactic space is a critical first step for exploration. Advanced sensors and telescopes could identify gravitational currents and void regions, creating navigational maps for spacecraft. These pathways would help optimize fuel use and avoid unnecessary detours. Andromeda and other nearby galaxies may contain Earth-like planets or other hospitable environments. Identifying these locations would be a major focus of intergalactic exploration. If suitable habitats exist, they could serve as bases for further expansion or as new homes for humanity. Quantum entanglement could revolutionize communication across intergalactic distances. Unlike traditional signals, which take millions of years to travel between galaxies, entangled particles might allow for instantaneous communication. While this remains speculative, it could solve one of the greatest challenges of intergalactic exploration. Leaving the Milky Way would fundamentally change how humanity sees itself. No longer confined to one galaxy, we would become an intergalactic species, rethinking concepts of culture, identity, and purpose. This transition might unify humanity under a shared vision of exploration and survival. The anticipated collision between the Milky Way and Andromeda offers a unique opportunity to study galactic interactions. As the two galaxies merge, their stars and planetary systems will shift, potentially creating new opportunities for exploration and settlement. What does it mean to leave behind the galaxy that gave rise to humanity? Such a journey raises questions about our place in the universe and what we hope to achieve. Are we searching for survival, knowledge, or something more profound? These questions will shape the goals and ethics of intergalactic travel. Intergalactic travel represents the pinnacle of human ambition. It challenges our understanding of physics, biology, and engineering, pushing us to innovate in ways we can't yet imagine. If successful, it would mark humanity's greatest achievement, proving our ability to overcome the universe's vastness and securing our place among the stars. In this monumental task, every step forward is both a challenge and an opportunity, revealing not just the limits of the cosmos, but the boundless potential of human ingenuity. The infinite frontier. The infinite frontier represents the ultimate exploration, both physical and intellectual. Unlike a boundary we can touch or see, it moves as we progress, constantly reminding us of how much there is yet to uncover. The universe offers more than just physical space. It reveals layers of mystery about existence, laws of nature, and the human role within it. The infinite frontier isn't just about where we go. It's about the questions we ask and the answers we pursue. The distance to the nearest star feels overwhelming, yet it's only a fraction of the cosmic expanse. Distances expand into the unknown, making the concept of infinity almost impossible to grasp. The observable universe, limited by the speed of light and the age of the cosmos, only hints at what's beyond. Beyond our telescope's reach lies an unobservable expanse, a horizon we cannot yet breach. It's not just about traveling further, it's about imagining what lies there and finding ways to glimpse the unseen. The concept of infinity can be daunting. It implies no end, no edges, and no final answers. As the universe expands, galaxies drift further apart, stretching the boundaries of what we can hope to reach. The ever-accelerating expansion means regions of space are moving faster than light relative to us, placing them forever beyond our reach. Yet, this doesn't deter exploration. Instead, it motivates new methods to look beyond our current abilities, aiming to understand more about this boundless reality. One aspect of infinity is its abundance. The Milky Way contains hundreds of billions of stars, but it's one of hundreds of billions of galaxies. The numbers are staggering. Even among the stars, countless worlds orbit in configurations we've yet to imagine. Planets with conditions wildly different from Earth likely exist in abundance, and some may harbor life or offer clues about how life forms. Every discovery expands our perspective and pushes us to redefine what's possible. The idea of multiple universes adds another layer to infinity. Theoretical models like the multiverse suggest our universe could be one of an infinite number, each with different physical laws or constants. These universes could exist parallel to ours, or be completely separate, creating a web of realities we can barely conceptualize. This shifts the infinite frontier from being merely physical to encompassing possibilities far beyond our universe's structure. Human curiosity drives the push toward infinity. We explore not because it's easy, but because we must know what lies beyond. Every new frontier, whether it's a distant planet or a theoretical boundary, sparks innovation and new questions. The infinite frontier challenges us to think differently, to find ways of understanding concepts that may never fully make sense. This isn't just a journey of discovery, it's a journey of transformation, where each step changes how we see ourselves and our place in the cosmos. Our technology evolves with each frontier we reach, but it also reveals limitations. The tools that brought us to one milestone often can't take us to the next. Exploring the infinite frontier means constantly inventing new technologies, from propulsion systems to methods of data collection and analysis. As distances grow, so do the challenges of communication, navigation, and survival. Yet each breakthrough provides not only a step forward in space exploration, but also practical applications on Earth. Beyond the observable universe lies the greatest mystery. If we could see beyond the cosmic horizon, what might we find? It could be more galaxies, or it might be something completely different, a new kind of space, an entirely new structure of reality. This is where the infinite frontier takes on a philosophical dimension. What does it mean if we can never reach these places? And how do we reconcile that with our desire to understand everything? Dark matter and dark energy dominate our universe, yet we know almost nothing about them. They are invisible and interact with normal matter in ways that are still largely theoretical. These components represent an unexplored frontier, one that may hold the key to understanding the universe's true nature. Without grasping dark matter and energy, we are only scratching the surface of what the cosmos really is. Philosophical questions naturally arise when confronting infinity. What does it mean to live in a universe without limits? Does infinity imply that everything that can happen will happen somewhere? These ideas aren't just abstract. They influence how we frame scientific questions and interpret our findings. Infinity isn't just a concept, it's a challenge to human thought, forcing us to stretch our minds beyond what we're comfortable with. Interestingly, the human mind mirrors the infinite in its capacity for imagination and creativity. While the physical universe may be boundless, so too are the ideas we generate to understand it. This intellectual infinity is what allows us to explore concepts like parallel universes or theoretical physics. Our ability to think beyond what we know is perhaps the greatest tool we have for navigating the infinite frontier. Ethical considerations become more complex the further we explore. If we encounter new ecosystems or forms of life, what responsibility do we have to protect them? Do we prioritize human expansion or the preservation of cosmic diversity? These questions don't have easy answers, but they're vital as we push further into the universe. The infinite frontier isn't just a space of possibility, it's also a space of responsibility. Exploration isn't without risk. The infinite frontier is filled with unknowns, from physical dangers like radiation to existential threats like hostile environments. As we move further away from Earth, the stakes grow higher. Yet these risks are part of what makes the journey meaningful. Overcoming them requires ingenuity, preparation, and a willingness to face the unknown. Progress along the infinite frontier isn't about reaching an endpoint. There will always be more to discover, more questions to answer, and more challenges to overcome. This redefines progress itself. It's not about finishing the journey, but about continuing it, embracing the process of exploration as its own reward. The infinite frontier teaches us that the journey is as important as the destination. As interstellar travel becomes feasible, the focus will shift from nearby stars to distant galaxies. Each step expands the scope of what humanity can achieve. Intergalactic exploration transforms the infinite frontier from a cosmic boundary into a realm of unimaginable possibility. It's not just about finding new worlds, it's about understanding how galaxies interact, evolve, and connect within the universe. The infinite frontier also ties time and space together in unique ways. Infinite distances mean dealing with immense timescales, forcing us to think in terms of centuries or millennia instead of years. This shifts the perspective on exploration, making it a multi-generational endeavor. Each generation adds to the journey, contributing to a legacy of curiosity and discovery. Even within an infinite universe, cycles exist. Stars are born, live, and die, contributing to the formation of new stars and planets. Galaxies collide and merge, creating new structures. This cosmic recycling suggests that infinity isn't static, it's dynamic, filled with processes that continually shape the universe. Understanding these cycles gives us insight into how the cosmos sustains itself over unimaginable timescales. Different cultures and civilizations bring unique perspectives to the idea of the infinite frontier. Some see it as a space of opportunity, while others view it as a sacred mystery. These interpretations influence how exploration is approached and prioritized. Incorporating diverse viewpoints ensures that the journey towards infinity is as inclusive as it is ambitious. Long after Earth is gone, the knowledge and discoveries made along the way will endure, shaping the story of our species. Exploring the infinite frontier isn't just about survival, it's about creating meaning, ensuring that humanity leaves a mark on the universe that will never fade. As we journeyed through the cosmic neighborhood, from the intriguing Alpha Centauri system to the challenges of interstellar travel, it's clear that the stars hold both inspiration and immense hurdles. Proxima Centauri and its rocky companion Proxima b remind us of the delicate balance between hope and harsh reality in the search for life beyond Earth. The vast distances, staggering timescales, and unyielding physics of the universe challenge us to think bigger, innovate further, and dream beyond the limits of what seems possible. Each star, every light year, and the immense gulf of space between remind us of humanity's resilience and curiosity. The cosmos may seem unreachable, but every step forward brings us closer to turning the impossible into reality. Make sure to subscribe to the channel if you enjoyed the video, and stay tuned for more adventures into the mysteries of the universe. Thanks for watching.